Attention please. Ladies and gentlemen. Vyacheslav Shulunov presents Breakthrough 3D Bioprinting Technology. Roll porous scaffold, new hope for overcoming the shortage of organs for implantation and rejuvenation of the whole organism due to the forming of your own endocrine glands. According to the report of the company Market Research Future, the 3D bioprinting market was estimated at United States dollars 87 billion in this year and is projected to grow to 9.41 billion by 2032, demonstrating a compound annual growth rate of 15.98% during the forecast period. Large companies in many countries are investing heavily in research and development and are driving further growth in the 3D bioprinting market. The next slide shows the currently dominant bioprinting methods. First, extrusion, based on syringe. Second, droplet, based on inkjet. Third, laser bioprinting. The following video shows the sequence of bioprinting organs using the spheroid extrusion method. Here is an example of a new generation syringe bioprinter capable of creating complex structures using tissue spheroids and a wide range of hydrogels with various polymerization mechanisms, including thermo, photo, pH and ion-sensitive hydrogels, as well as mixtures of various hydrogels. There is another, super technological and expensive, 3D bioprinting technology, implemented by Russian scientists from 3D bioprinting solutions. This device makes it possible to bioprint bone tissue in space by growing fragments of the bone structure in zero gravity. During experiments on the ISS, tissue samples were made from calcium phosphate ceramics, which were populated with living cells. The following video will show its details. Roll porous scaffold 3D bioprinting combines the best time-tested extrusion, inkjet, and laser technologies. New methods solve the fundamental problems of quickly bioprinting with high precision and multiple cell types simultaneously in large volumes by hundreds of thousands of nozzles instead of one laser or 6 syringes. This way make possible to reach organoid density more than 1 million cell per milliliter with performance liters per hour. Bioprinting organs are much more complex than skin, and cartilage requires vascularization to transport nutrients, oxygen, and waste products. Achieving these goals with modern bioprinters is difficult due to complex, heterogeneous biostructures with micro and macrovascularization. Bioprinting of small capillaries is difficult because current technology allows the creation of vessels only greater than 100 micrometers in diameter. This slide shows a simplified sequence of transformation of filled tape into tubular object by its winding in roll. When object is formed, the roll placed under water. Then, support ribbon is solved and object is ready. Therefore, for building a multilayer tubular object, it is necessary to add many flat areas. For example, illustration: the transformation of a tape filled with 6 various components in order to form a multilayer tubular object from them in a wound roll. This picture demonstrates simplified consequence of forming multilayer tube with branches similar to blood vessels. However, it is possible to increase cell density by orders of magnitude in droplet bioprinting if to use the roll porous scaffold 3D bioprinter with a multi-component ribbon consisting of many layers, such as fine mesh support, porous, attachment, and auxiliary one. At first glance, inkjet technology cannot achieve the same cell density as extrusion or laser one, because in this case, it is necessary to increase cell concentration by 100 times, but it works at its limit of viscosity. A significant increase in cell density will lead to clogging of the nozzles. To increase the density of conventional ink bioprinting by 100 times and achieve density of million cells per 1 milliliter, it is suggested to pass this flow through a fine sieve. Separation of cells from the 1000 picoliter flow occurs using a 3737 micrometers comb with 49% transparency, surrounded by 5 micrometers edging. Drops with volume of approximately 5 picoliter can easily pass through this area. Thanks to a grant from the Foundation for Assistance to Innovations, many laser-perforated samples of water-soluble supporting films were made and tested. This slide shows the difficulties of laser perforation. It is difficult to determine the pulse frequency, their power and exposure, etc., together with the speed of specular reflection. increasing the density of laser beams, selecting the times of their switching on and off, and the number of repetitions allows us to improve the shape of the perforations and increase their quality. The distances between cells determine their interactions and tissue growth. For a pair of the smallest 10 micrometers cells, the maximum distance is 17 micrometers, and for 15 micrometers 7 micrometers in the adjacent layer, and within its comb accordingly. The biggest for cells, size of approximately 8 micrometers, will occupy approximately 7 picoliter of a 32 picoliter comb voxel, and there is enough space for them to proliferate.
Here is general basic view of roll porous scaffold 3D bioprinter. First, the tape is precisely rewound from roll 1 to roll 2 by rollers 3 and 4 using a tension control system 5. Then the drip filling system 6 fills it with various bioinks in accordance with the required tissue from a plurality of reservoirs installed above it. Excess ink water is removed by a drainage system 7. When the frame has been formed and filled with nutrient fluid from tank 12, it is covered with tape 9, separating the layers. The supporting foil is wound on a roll 10. The accuracy of the ribbon, reinforced and side perforated like cinema film, winding is controlled by the frame's position and merging control systems 8 and 11. Since the computed 3D CAD model of the bioprinting object is divided into frames, the position of all of them on the scaffold ribbon is known in advance by the length. The system verifies actual and planned location for each frame. To correct possible distortion, the next one is shifted, by software, forward or backward according to the location of the marks.
Years ago, a linear printhead, suitable for bioprinting, was made. This model provides resolution 1200 dpi, minimum drop volume 1.5 picoliter, maximum drop volume 2.8 picoliter, with maximum jetting frequency 80 kHz. Next video shows advantages of piezoelectric inkjet printhead and roll-to-roll printer. This comparison shows that roll porous scaffold technology has the best of the currently dominant bioprinting ones for low cost. The problem is, in inkjet bioprinting technology, each cell in the bioink must be surrounded by a liquid volume of 1000 tcl to guarantee fluidity. So, by decreasing the speed of the tape from 100 meters per minute down to approximately 5 millimeters per second and removing excess water, it is possible to surpass extrusion cell density. Combining these advantages in a single device makes it possible to create multicellular systems with high precision, equipped with vascular and neural networks, which cannot be achieved using traditional, dominant bioprinting technologies. It should be noted that albeit roll porous scaffold is a project and never used, it is a derivative of the time-tested methods and components of bioprinting. Therefore, following specifications are achievable: cell density exceeds extrusion and laser 3D bioprinting, performance, liters per hour, layer thickness, approximately 18 micron, print volume, approximately 5 liters. In 3D bioprinting, there are major challenges with nutrient and metabolic waste transport systems, blood supply, neural networks, and long-term survival of cellular structure. Roll porous scaffold offers solutions to these problems. New methods designed to assist organ-on-a-chip technologies, personalized medicine, targeted therapy, and individualized hormone replacement therapy. It is logical that youth will return even after 100 years if the level of hormones is restored. For example, make endocrine glands for each person from his own DNA so that there is no rejection. After tens of years, repeat this procedure, and hello eternal youth. Thank you for your time.